Hello everyone, and thanks for joining us on today's webinar on EMI EMC in Automotive Systems. My name is Amin. I'm an Alpha Application Engineer at EMWorks. So before we start, I would like to give you a short summary about what we are going to discuss today. So first, we'll talk briefly about some of EMI issues as well as some sources of EMI in modern vehicles. After that, we'll look at some ways of reducing EMI along with some EMI and EMC standards. At the end, we'll have a live demo. So in case you have any questions, I'll be happy to answer them at the end of the presentation. Before we go ahead, I would like to give you a short introduction about our company, EMWorks. EMWorks is an electromagnetic simulation software company based in Montreal, Canada. We cover both low and high frequency applications. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, transformers, and power electronics to antennas and various wireless circuits and components. Alright, now let's talk about some of EMI issues in modern vehicles. In contemporary vehicles, the surge in electronic components and wireless technologies has intensified EMI and EMC concerns. These issues stem from both internal factors like the close proximity of electronic systems and external sources including nearby broadcasting towers. The coexistence for components like Wi-Fi, Bluetooth, satellite, radio, GPS systems, air conditioning, power steering, anti-lock brakes, and other intricate systems within confined spaces can lead to interference problems. Analyzing and mitigating EMI and EMC are crucial to ensure these components function seamlessly alongside each other. Unchecked interference may lead to communication errors, malfunctions, and compromised safety features. Manufacturers must incorporate effective shielding, filtering, and guarding techniques during design and testing to meet EMC standards. This ensures that the diverse electronic systems in modern vehicles operate cohesively, upholding safety and performance standards. Next, we'll examine some sources of electromagnetic interference. EMI in automotive environments arises from diverse sources. Wireless communication systems such as Wi-Fi and Bluetooth can introduce interference due to their radio frequency signals. Inadequately shielded or improperly routed cables and wiring may act as antennas, picking up and radiating EMI. Moreover, charging systems, including alternators and voltage regulators, can introduce electrical noise in the vehicle's electrical system. Electric motors can also be a source of EMI. They are used in various vehicle components such as power steering, windshield wipers, and electric windows and can generate noise during operation. Additionally, switching power supplies can produce high-frequency noise, adding to EMI challenges. Lastly, external sources, including radio and TV towers, can also introduce interference. Managing and mitigating these sources is crucial for ensuring the proper functioning of electronic systems within vehicles. The right image illustrates different sources of EMI in automotive environment. Now, let's dive into some types of EMI. In automotive systems, electromagnetic interference manifests in both conductive and radiative forms, presenting unique challenges for electronic systems. Conductive EMI often occurs when physical contact or proximity allows unwanted electrical currents to disrupt electronic circuits. Example in automotive settings include poor grounding or faulty cables that lead to interference in communication systems or cause malfunctions in powertrain electronics. Radiative EMI, on the other hand, involves the propagation of electromagnetic waves through the air. Common examples in vehicles include wireless communication systems such as Wi-Fi and Bluetooth and GPS systems. The coexistence of conductive and radiative EMI sources requires comprehensive strategies, including proper shielding, grounding techniques, and adherence to EMC standards to ensure the seamless operation of electronic systems in the automotive environments. Next, we look at EMI, EMC. Electromagnetic compatibility is a crucial aspect of electronic system design, referring to the ability of devices to operate efficiently without causing or experiencing interferences in the presence of electromagnetic fields. EMC is ensured through a battery of tests, including radiative emission tests, which measures the electromagnetic waves emitted by a device. The radiative immunity test assesses the device's resilience to external electromagnetic fields. The conducted emission tests measure the electromagnetic noise transmitted via power and signal lines, while the conducted immunity tests assess the device functionality when subjected to conducted interference. In the automotive sector, adherence to standards like CI, SPR 25, FCC Class A 10 meter, and ISO 11452 is critical. These standards set guidelines for electromagnetic compatibility, ensuring the integrity and functionality of electronic components in vehicles. The table on the left demonstrates the radiation emission limits according to FC Class A standards. Now that we have explored EMI, EMC, let's look at some ways to reduce EMI. Addressing electromagnetic interference issues in electronic systems involves implementing several essential techniques. Proper cable routing and shielding play a crucial role, as organized and well-routed cables along with shielded conductors help minimize the potential for electromagnetic emission and susceptibility. Careful design of ground plane is another essential consideration, providing a low impedance path for straight currents and reducing EMI risk. Furthermore, the integration of EMI filters can effectively suppress unwanted high-frequency noise, ensuring cleaner power and signal lines. Strategically placing components is another key method for minimizing the loop area of current flow, effectively reducing electromagnetic radiation. By incorporating these techniques into the design process, engineers can significantly enhance the overall electromagnetic compatibility of electronic systems, mitigating the impact of EMI. That concludes our discussion on EMI suppression. Next, we'll talk briefly about the importance of electromagnetic simulation. EM simulation emerges as a crucial tool in mitigating electromagnetic interference issues within modern vehicles. Through comprehensive frequency analysis, EM simulations enable engineers to assess the frequency behavior of electronic systems, ensuring that the electronic systems operate within desired frequency bands without causing interference or being susceptible to external sources. Virtual simulation can also reduce the need for physical prototypes and extensive testing, saving both time and cost in the development process. Early detection of EMI issues is another key advantage, allowing engineers to identify and rectify potential electromagnetic interference challenges in the design phase, preventing costly modification in later stages. Additionally, EM simulation plays a pivotal role in ensuring compliance with EMC standards, thereby enhancing the overall reliability and performance of electronic systems in modern vehicles. Now that we have discussed some key advantages of employing EM simulation, let us look at an example of EMI in the automotive industry. As we can see, we have power cables that are 2 meters in length and they are placed inside the car. Our focus will be on examining the EMI issues arising from common mode noise. Throughout the upcoming slides, we will explore key aspects of this case study, including crosstalk, radiated emissions, and immunity testing. By analyzing these elements, we aim to gain insight into the impact of common mode noise on power cables and associated challenges in mitigating EMI in electronic systems. First, let's take a closer look at the crosstalk. Crosstalk between power cables in the vehicles refers to the unwanted electromagnetic coupling between these cables, leading to interference and potential performance issues. In the context of power cables, there are two primary modes of interference: common mode and differential mode. Common mode interference is often of greater concern. This is because common mode noise can induce high level of electromagnetic interference and impact the overall performance and reliability of electronic systems in the vehicle. Common mode currents can easily flow through the vehicle metal structure, increasing the potential for interference with other electronic components and communication systems. Observing the two graphs, it is evident that the common mode aggressor produces high level of electromagnetic interference in the victim line when compared to differential mode. On this slide on the left, we can see the electric field animation both on the aggressor and the victim line at the resonant frequency of 76 MHz. Besides crosstalk, radiated emissions from power cables represent another type of EMI that can impact the functionality of automotive systems. The investigation of radiated emissions from power cables in vehicles induced by common mode is crucial in ensuring electromagnetic compatibility. When the physical lengths of this cable reach lambda over 2 or multiple lambda over 2, they can function as unintentional antennas emitting electromagnetic waves. This phenomenon poses significant risk of interference, potentially disrupting the proper functioning of electronic systems in the vehicles. Looking at the two graphs, it is apparent that at 76 MHz, the power cable attains resonance. As a result, they emit more electromagnetic radiation compared to the emission level observed at 20 MHz. By studying and addressing these radiated emissions, engineers can implement effective measures to minimize electromagnetic interference, guaranteeing the reliable operation of critical vehicle electronic and systems. Having explored crosstalk and EMI in power cables, let's now delve into the topic of immunity testing. Immunity testing in the automotive environment is a crucial aspect of ensuring the robust performance and reliability of electronic systems within vehicles. As automobiles are exposed to various electromagnetic fields and radio frequency interference, immunity testing evaluates the resilience of this system to external disturbances. This testing assesses how well automotive electronics can withstand interference, such as electromagnetic pulses or radio frequency signals, without experiencing malfunctions. In this example, the power cables and the car are positioned within a semi-anechoic chamber to assess the performance of the cable and the varied levels of electric field severity generated by the biconical antenna. The left plot illustrates the electric field severity levels generated by the antenna, while the right plot displays the distribution of the E field during the operation of power cables in the presence of the antenna. Examining the right plot at 20 MHz reveals minimum changes in the E field distribution for varying external E field intensity levels, demonstrating resilience to external disturbances. Let us now see what would happen to the field distribution at the resonant frequency of 76 MHz. At resonance, the power cables function as unintentional antennas receiving an increased EM radiation compared to 20 MHz. This induced voltage causes clear shift in the E field distribution, as we can see on the right. In this slide, you can again observe that the power cables at 20 MHz show resilience to external disturbances caused by the biconical antenna. Contrarily, at 76 MHz, we can clearly notice a destructive interference caused by the antenna. So as we can see, there's a big drop in terms of the electric field. So basically the electric field dropped from a value of 500 volt per meter to almost 400 volt per meter. So you can clearly see there is big change in terms of the electric field intensity. The same conclusion can be drawn from this slide. So basically at 20 megahertz, the power cables operate effectively. However, as the cable approach lengths comparable to the wavelength, they begin to function as antennas, both receiving and transmitting interference to nearby automotive devices, as we can see on the right. Welcome again in this live demo. In this demo, we'll show you how to conduct EMI, EMC analysis using HFWorks. So as you can see, HFWorks is fully embedded inside SolidWorks. Once you finish creating your geometry inside SolidWorks, you can just go ahead and start your EM simulation using HFWorks. So just simply a tab. For today's analysis, we have two configurations, one for EMI and one for EMC. We'll talk about this more later. So first, let's start with the EMI analysis. For the EMI analysis, we have two associated studies. We have crosstalk and radiated emissions. In HFWorks, we have four types of studies. We have antennas, S parameter, TDI, and resonance. But today, we'll focus on antennas and S parameter. Like any other electromagnetic simulation software, we usually have three main steps. First, we need to specify the operating frequency range, apply material, and then assign boundary conditions. So first, let's start with the frequency settings. So once you right-click, we go to Properties. So under this table, we can specify, for instance, the level of accuracy, whether it's normal or high. Also, we can specify whether also interested in 3D field data, such as electric and magnetic field. As for the frequency sweep, we have different types of sweep. We have discrete, we have fast, single point. Also, you can import your frequency point from file if you have it. So for discrete sweep, so for instance, for this example, we have the start frequency of 20 megahertz and end frequency of 100 megahertz. We have 21 frequency points. As for the meshing, we have two types of mesh. We have manual mesh and the adaptive mesh. For the adaptive mesh, the software will try to find the appropriate mesh for your structure. However, if you are an experienced user and you know where to apply mesh control in your structure and you want to save some time on the meshing time, you can use the manual mesh. As for the coupling, if you are interested for instance, studying the temperature distribution in your structure, you can click on the thermocoupling. So next, let's look at the materials. In HFWorks, we have our material library, which consists of a large number of materials with predefined properties, as you can see. You can create a new material library, or you can even import your material library if you have one. As for the boundary conditions, we have different types of boundary conditions. We have port, we have lumped port, we have lumped elements, PEC, PMC, we have PEC symmetry, PMC symmetry. Also, we have the radiation boundary. Next, let's look at the mesh control. If you choose to go for the manual mesh, you have the option to apply mesh control on bodies. For instance, you can apply mesh control on the body of the car. You can apply mesh control on the face, and also you can apply the mesh control on the edges, as we can see. You can also specify the element size. So back to our model. So as you can see, we have a car, and inside the car we have 4 power cables. So as for the materials, If you want to edit, for instance, the material properties, you can simply right click and set edit material. So on this table you can edit the material property that you're interested in. For instance, you can change permittivity, loss tangent, electric conductivity, dielectric strength, permeability, along with other parameters. So for this car, as I said, so we have a car. Inside we have 4 power cables, and also we have our radiation boundary. So as for the boundary conditions, so we have 4 wave ports, as we can see. This is first port, this is second, this is third, and this is fourth. Also we have the radiation boundary. So to assign port, you simply right click and you choose port, and then you can select, for instance, this face as wave port, and also you can specify whether the port is external or internal. For instance, in our example, since the port is inside the computation domain, so we choose internal. Also you can specify the type of port, whether it's normal port or differential port. Also you can specify the number of modes. Maybe I need to show the car, I need to see the mesh. So if you right click, you say show mesh. So now we can see the mesh. Also, can see, if we can hide the car, so you can see now the mesh, both in the ground plane and also along the power cables. Alright, so let's look at some of the simulation results. In HFWorks, we have what we call the results table. The results table basically gives a summary of circuit parameters such as generalized ACE matrix, renormalized ACE matrix, impedance matrix, admittance matrix, port result, and VSWR. You can print results versus current or off frequencies. You can export data, results to different formats such as text, CIT, SPC, or touchstone. Also, we have the 2D plot for different parameters, such as S parameter, impedance, admittance, VSWR, along with other parameters. So first, let's look at some of the 2D plots. So in this plot, we can see the common mode crosstalk, both the near and far end crosstalk. Also we can see the differential mode crosstalk. So to create this plot, you simply right click, you choose 2D plot, and then for instance, let's say you are interested in seeing, for instance, the differential mode crosstalk. Yeah. So also you can see the data in the tabular format. You can export again results to different formats, such as text and CSV. Also you can see the electric field along with the magnetic field. If you want to animate, we simply right click, we said animate. So now we can see the animation of the electric field. Also we can see the port electric field. So for instance, for this one, for port 1, let's say we choose mode 2, which corresponds to the common mode. So now we can clearly see the common mode. Also you can see the differential mode in a vector format. So also we can specify the operating frequency. Now let's look at the radiated emissions study. So again, we have the car, and inside the car we have 4 power cables, as we can see. But this times, for port 2 and 4, we set them as a lumped port, having impedance of 450 ohms, as you can see. So now let's look at the electric field distribution, both at resonance and also at 20 megahertz. So for this, we need first to show the air. So now we can see the electric field distribution, which is generated by the common mode aggressor. Also, we can change the plane for the electric field. Now we can see the electric field distribution for the aggressor line at 20 megahertz. So to create this field, you simply right click, you go to 3D fringe plot. So we can choose no clipping, section clipping, or iso clipping. For this, we wanted, for instance, section clipping. So for the electric field settings, we can specify, for instance, the operating frequency, let's say 20 megahertz, and also we can specify which port we want it excited. For instance, we want port 1 to be excited with mode 2, which corresponds to common mode. And also we can choose the section clipping. So for instance, we can change the plane, and for instance, we want plot on section only. Yeah, so now we can also see the gray model. Also we can edit the electric field chart levels. For instance, let's say we want it maybe to be 25. Yeah, so now we can clearly see the electric field. Yeah. Now let's look at immunity testing study. So for this study, as we can see, you have the biconical antenna, you have the 4 power cables, you have the semi-anechoic chamber, and also we have the car. I need to show the car. Yeah, so now we have the car. So now let's look at some of the simulation results. First, let's start with the far field parameters. In HFWorks, we have what we call the far field antenna parameters. So basically, this table summarizes some of the important antenna far field parameters, such as maximum directivity, maximum gain, radiation efficiency, as well as the total efficiency. We can again export results to different formats, as you can see. Now let's look at the 3D radiation pattern of the biconical antenna. So now we can see the 3D radiation pattern of the biconical antenna. Maybe I need to hide the absorbers. Yeah, so now we can clearly see the 3D radiation pattern of the biconical antenna. So in order to see the induced electric field by the biconical antenna, I tried to, maybe I need to hide the car. Yeah, so basically I tried to create 3 points, as we can see, along the victim line. So this is the aggressor line and this is the victim line. So now, for instance, we can see the induced electric field by the biconical antenna for different input power for the antenna. So to create this plot, so we right click, choose 2D plot, linear. So first we need to specify the frequency. So now I want, let's say, 1000 points between these 3 points. So for this, since I want to see the induced electric field by biconical antenna, so I only need to excite the antenna. Now I put now input power of 1 watt. So now I can see the electric field distribution along 2 meter power cable. So in order to see to compare the electric field induced by the antenna for different input powers, in order to compare that, I need to import the data. So first, for antenna at 10 watts, so for instance for 10 watt, you can see the induced field by the biconical antenna. Same thing for 20 watts. So for instance at 20 watt, so we can see the induced field of almost 0.3 volt per meter. So now, in order to see the operation of the power cables in the presence of biconical antenna, so basically I need to excite both the antenna and the power cables. So for this, I need, again we go to 2D plot, linear. So I need to import the points first. So I put 1000 points. So this time I need to excite the antenna. Also I need to excite port 2 with mode 2, which corresponds to the common mode. And now I can compare with other studies, just as. So now for this, we excite the antenna with 10 watt and also with 20 watt. So now we can clearly see that the power cables at 20 megahertz show resilience to the external field which are generated by the biconical antenna. Alright, so let's look at the 3D electric field. Okay, so for now I need to show the semi-anechoic chamber. As well as the ground floor. So first, let's look at the study of 20 megahertz. So now we can see the field distribution. So for this case, both the biconical and the power cables are excited. So to animate, we simply right click, set animate versus phase. So now, yeah, so we can see so for these examples, as we can see, both the antenna and the power cables are excited. So power cables are excited with mode 2, which corresponds to the common mode. Similarly, at the resonance, so we can see that those power cables now act as intentional antennas receiving and transmitting interference. So if we right click, we can now we can see clearly the animation of the electric field. Also, we can see the distribution of the electric field along the cables at 20 megahertz, same thing as 76. We can again animate it. In summary, you have learned about some of EMI issues associated with automotive power cables. We have showed you the importance of employing 3D simulation software like HFWorks for early detection of EMI concerns. This enables engineers to identify and address potential electromagnetic interference challenges during the design phase, preventing the need for costly modifications in later stages. With that, I would like to thank you, and now the floor is open for questions.